Okay, welcome back. And today we'll see the properties of Fourier transform. So in the last two videos, I have discussed how we arrived at Fourier transform and why Fourier transform, and how we started with Fourier series and how we arrived at Fourier transform. And we have seen what is the Fourier integral and the Fourier coefficient density, all those things. And today we'll discuss around 11 properties, and things are very simple and very important also. So first we'll see linearity property. So linearity property, we know that is they have to obey the principle of homogeneity as well as superposition. So we are considering those two principles in this linearity. And if x1 of t leads to x1 of j omega, so what is x1 of j omega? X1 of j omega is nothing but the Fourier transform of x1 of t. Likewise, x2 of j omega is the Fourier transform of x2 of t. Then we have a linear combination of those two signals, that is a is being multiplied with x1 of t, that is obeying the principle of homogeneity. Then b is being multiplied with x2 of t, again homogeneity principle. And then we are superimposing those two signals, that is a x1 of t plus b x2 of t. And if we find the Fourier transform of such a signal, then that is simply a of x1 of j omega plus b of x2 of j omega. So that is, it obeys the principle of linearity. Okay, so how will you prove that? That is, by definition we know what is x of j omega, that is equal to integration from minus infinity to infinity x of t e raised to minus j omega t dt. So instead of x of t we have the signal a x1 of t plus b x2 of t. We substitute that, e raised to minus j omega t dt is already there. Then we open the integration. A is a constant, so that will be coming outside the integration. So that is x1 of t. Then e raised to minus j omega t dt is common, so that is attached to x1 of t, plus b again comes out of the integration, and integration is from minus infinity to infinity. What is the remaining things are x2 of t e raised to minus j omega t dt. So what you see inside the integration, that is x1 of t e raised to minus j omega t dt, is nothing but x1 of j omega, and what you see inside the second integration is nothing but x2 of j omega. So that is how it is being proved. So it obeys the linearity property. And then the second property is the time shifting property. So what is time shifting property? That is, if x of t leads to x of j omega, then if we delay or if we shift the signal by t0 seconds, that is x of t minus t0, then what is the Fourier transform of such a time shifted signal? That is, it is nothing but e raised to minus j omega t0 x of j omega. So x of t minus t0, if we find the Fourier transform, it is nothing but e raised to minus j omega t0 x of j omega. So again we have to prove that. So by definition we know that is x of j omega is equal to, that is Fourier transform of a signal x of t is nothing but x of j omega, which is equal to integration from minus infinity to infinity x of t e raised to minus j omega t dt. So instead of x of t we can substitute x of t minus t, x of t minus t naught. Everything remained, every other all terms remain the same, that is x of t minus t naught multiplied by e raised to j omega t dt. Now one technique we usually use is that we replace t minus t naught by a dummy variable p. So if t minus t naught is equal to p, then what is t? T is nothing but p plus t naught. So if you want to substitute instead of t minus t naught a dummy variable, we have to make the integration with respect to p, as well as we have to change the limits of integration also with respect to p. So if you differentiate both sides of t is equal to p plus t naught, we have t is equal to p plus t naught. If you differentiate both sides, we get t dt is equal to dp, because t naught is a constant, that becomes 0. So dt is equal to dp. So instead of dt we can simply substitute dp. And what about the limits of integration? See, we know t is equal to p plus t naught. So when t tends to minus infinity, p also will tends to minus infinity. If t tends to plus infinity, then p also will tends to infinity. So limit of integration will remain the same. So we substitute everything in that integration. So integration is from minus infinity to infinity x of, instead of t minus t naught we have p, then e raised to minus j omega, then we have e raised to minus j omega t is there. So instead of t we substitute p plus t naught, and instead of dt we substitute dp. Okay, now we open the brackets of e raised to minus j omega we have e raised to minus j omega p multiplied by e raised to minus j omega t naught. So our integration is with respect to p. So in that sense, e raised to minus j omega t naught is a constant. We can bring that outside the integration, and inside the integration we have minus infinity to infinity integration x of t e raised to minus j omega p dp. So p is simply a dummy variable. You can simply replace p by t itself. So what you see inside that integration? So that integration is nothing but x of j omega. So e raised to minus j omega t naught x of j omega is nothing but the Fourier transform of x of t minus t naught. So there is one more implication from that result. That is, we have found the Fourier transform of x of t minus t naught. So what about the Fourier transform of x of t plus t naught? X of t plus t naught Fourier transform is nothing but e raised to j omega t naught x of j omega. So that's an implication from that result. Now coming to the third property, that is frequency shifting. So earlier in the second property we have done time shifting. So what about frequency shifting? See actually by Fourier series we are actually converting a signal from time domain to frequency domain. See, x of t is being converted to x of j omega. So what is j omega? Omega is nothing but a frequency. So there is no time terms in that Fourier transform. After finding Fourier transform, we don't find any time terms. So in that time domain, we don't find any frequency term. So we are actually converting a signal in time domain to frequency domain when we perform the Fourier transform. Okay. So if you want to shift frequency, we have to do that in frequency domain. So that is what is explained through this property, that is property number 3, that is if x of t leads to x of j omega, that is when we do the Fourier transform of x of t, if it leads to x of j omega, then what about if x of t is being multiplied with e raised to j omega naught t? So what about the Fourier transform of such a signal? The Fourier transform of such a signal is nothing but x of j omega minus omega naught. That is what I told. That is, we are shifting the frequency of the signal by omega naught. Then what we get in time domain is that x of t is being multiplied by e raised to j omega naught t. So when we shift the signal, the frequency by omega naught, then the corresponding signal x of t in the time domain is being multiplied with e raised to j omega naught t. We have to take that in that sense. Okay, so what about the proof? So by definition, we know what is x of j omega. That is already done and we have explained in numerous times. Then instead of x of t, we simply substitute e raised to j omega naught t x of t, and e raised to minus j omega t dt is already there. Then we combine the e raised to terms, that is x of t, e raised to minus j omega minus omega naught t dt. So what is x of j omega? That is x of j omega is nothing but e raised to integration from minus infinity to infinity x of t e raised to minus j omega t dt. So instead of so if that is e raised to minus j omega, so that is why we represent it as x of j omega, because in place of omega we have omega itself, but here we see that in place of omega we have omega minus omega naught. So we can use the definition to write it as, instead of x of j omega, instead of omega, as we have omega minus omega naught, we can write it as x of j omega minus omega naught. So that is the proof of that. That is e raised to j omega naught t x of t. We find the Fourier transform, we have x of j omega minus omega naught. That is this is how it has to be written or set. That is, if we frequency shift a signal in frequency domain, then what is the corresponding implication in time domain? Correspondingly, the signal x of t will be multiplied by e raised to j omega naught t in time domain. So that is another implication for that. That is, if x of t is being multiplied with e raised to minus j omega naught t, then that is simply x of j omega plus omega naught in frequency domain, or after finding the Fourier transform, that is the result. Okay. Now the fourth property, that is time reversal property. You can just simply find the derivation again. You will use a simple technique of dummy variable and all those things. You can just understand that. And if x of t leads to x of j omega, then x of minus t will lead to x of minus j omega. That is the property of time reversal. That is, if you reverse in time, that also happens in frequency domain. Then the very important property, that is fifth property, that is differentiation in time domain. Okay, that is, if x of t leads to x of j omega, then if you find the derivative of x of t, that is d by dt of x of t, then what is the Fourier transform? The Fourier transform of such a derivative of x of t is nothing but j omega x of j omega. J omega is being multiplied with x of j omega. So when you find the derivative, first order derivative of x of t, x of j omega is multiplied with j omega. That is what. Okay, so we'll prove that. So we'll prove in a different way. We know the inverse Fourier transform, that is, inverse Fourier transform of x of j omega is nothing but x of t. So if you want to retrieve the signal from frequency domain, if you want to retrieve the signal x of t from x of j omega, then this is the definition. That is, x of t is equal to 1 by 2 pi minus integration from minus infinity to infinity x of j omega e raised to j omega t d omega. So that is the inverse Fourier transform for the Fourier integral. And this is one thing we have already discussed in the last video. And so we differentiate both sides of that equation with respect to t. So d by dt of x of t equal to 1 by 2 pi. 1 by 2 pi is a constant that is coming out of the differentiation. D by dt of, inside the bracket, the whole thing, that is integration from minus infinity to infinity x of j omega e raised to j omega t d omega t. Okay, and again integration can be brought out of the differentiation. The reason is that integration is with respect to omega, and differentiation is done with respect to t. So in that sense, that integration, that is integration from minus infinity to infinity x of j omega d omega is a constant with respect to that differentiation. So that will be coming out. But you have to do the differentiation of d by dt of e raised to j omega t, because there is a term t there. Since we are performing differentiation with respect to t, we have to account that. And when you find the derivative of that, 1 by 2 pi is already there. Integration from minus infinity to infinity is already there, x of j omega. Then if you find the derivative of that, it is j omega e raised to j omega t d omega. Now we are performing the integration with respect to omega. So omega. So you can actually bring that outside, j omega 1 by 2 pi. If you bring that outside the derivative, j omega 1 by 2 pi, integration from minus infinity to infinity x of j omega e raised to j omega t d omega. So what is inside the bracket is nothing but x of the inverse Fourier transform of x of j omega, that is for f of j omega, f inverse of x of j omega. So d by dt of x of t is equal to j omega Fourier inverse of x of j omega. Okay, I hope you understand. That is what you see inside the bracket, that is 1 by 2 pi integration from minus infinity to infinity x of j omega e raised to j omega d omega is nothing but the Fourier inverse of x of j omega, or that is nothing but x of t. Okay, so that is why we have written Fourier inverse of x of j omega multiplied by j omega, that is equal to d by dt of x of t. Now if we find the Fourier transform on both sides, so Fourier transform of d by dt of x of t is nothing but, when you find the Fourier transform of the RHS, that Fourier inverse gets cancelled. What you get is j omega x of j omega. So that is the result of that. And there is another implication, very important implication, that is, if you find the nth order derivative of x of t, and if you want to find the Fourier transform of such a signal, then that is nothing but x of j omega the whole raised to n x of j omega. So very important result, very useful result. You may be using this result in many problems. Now coming to the sixth property. Now in the fifth property, we have done differentiation in time domain. And what happens if you do the differentiation in frequency domain? So frequency domain integration is done after performing the Fourier transform. Okay. So if x of t leads to the Fourier, if x of t leads to x of j omega, then what is the Fourier transform of t multiplied by x of t? That is nothing but j d by d omega x of j omega. That is, you can say that in a different way. That is, if you perform the first order derivative, if you perform the derivative with respect to frequency of x of j omega, then that corresponds to x of t b multiplied with t. Okay, then again the proof, by definition we know what is x of j omega. Again the same technique, that is differentiating the above equation with respect to omega. Okay, and we take that, and as we are performing the differentiation with respect to omega, the integration will come out, but the differentiation will be only done with respect to e raised to minus j omega t. And if you do that, you will get it as minus infinity to infinity x of t minus jt inside the bracket e raised to minus j omega t dt. Okay, now minus j you can take outside, and t and x of t is combined, x e raised to minus j omega t dt. So minus j, what is integration from minus infinity to infinity t x of t e raised to minus j omega t dt? That is nothing but the Fourier transform of x t into x of t. So minus j, Fourier transform of t into x of t. Okay, so we started with finding the derivative of x of j omega. So d by d omega x of j omega equal to minus j Fourier transform of t x of t. That means you can bring that minus j to the other side. When you bring the minus j to the other side, it becomes 1 by minus j d by d omega x of j omega. So 1 by minus j is nothing but j. So that can be written as j d by d omega x of j is nothing but the Fourier transform of t x of t. Okay, I repeat that minus j you can bring to the other side. When you bring the minus j to the other side, it becomes 1 by minus j. 1 by minus j is nothing but j. So j d by d omega x of j omega equal to the Fourier transform of x of t. So for the Fourier transform of t x of t is nothing but j d by d omega x of j omega. Now the seventh very important property, the convolution property, and we know what we do in a convolution. Okay, that is, if x1 of t leads to x1 of j omega, and if x2 of t leads to x2 of j omega, then if we convolve those two signals in time domain, what happens correspondingly if we find the Fourier transform? So it's a very important result, that is, if we convolve two signals in time domain, that is simply the multiplication of those two signals in frequency domain. That is, if you want to convolve two signals in time domain, you simply find the Fourier transform of those two signals individually and you simply multiply. That is, x1 of j omega is simply multiplied with x2 of j omega. We'll get the convolution in time domain. That's a very important result. So if in a competitive examination, if someone asks to find the x1 of t convolution with x2 of t, the very easiest way of doing things is that you simply find the Fourier transform of x1 of t, that is x1 of j omega. Then you find the Fourier transform of x2 of t, that is simply x2 of j omega. Then you simply multiply x1 of j omega and x2 of j omega. Then you find the inverse Fourier transform of that signal. Then you get the convolution, convolved signal of x1 of t convolved with x2 of t. You get the result of convolution in time domain. That's the easiest way of doing things. Now, what is convolution? So x1 of t convolved with x2 of t is nothing but integration from minus infinity to infinity x1 of tau, that is a dummy variable, x2 of t minus 2 d tau. This was the result we found in the first module. We have discussed that convolution in detail then. Okay, therefore the Fourier transform of such a signal is that, see, Fourier transform, we know the signal multiplied with the integration of from minus infinity to infinity, the signal, then that is multiplied with e raised to minus j omega t dt. So what is a signal? That signal is done in the square bracket, that is integration from minus infinity to infinity x1 of tau, x2 of t minus 2 d tau. Now this is a usual technique, that is interchanging the order of integration. That is, x1 of tau is taken outside, d tau will be the last integration. The integration with respect to tau will be the last integration, and within the main integration, the first integration that we do will be, that is the integration from minus infinity to infinity x2 of t minus tau e raised to minus j omega t dt. Okay, then we employ the usual technique, that is replace t minus tau by a dummy variable p. From that we know what is t, that is p plus tau, and then when we want to replace that with a dummy variable, we have to convert everything with respect to the dummy variable p. So if you differentiate t is equal to p plus tau both sides, then that is equal to dt is equal to dp. Then What about the limits? Limit will remain the same because as t tends to minus infinity, p will also tends to minus infinity, and if t tends to infinity, then p also will tends to infinity. So integration will remain the same. So replacing everything inside the square bracket in terms of the dummy variable. So that is integration from minus infinity to infinity, x2 of p e raised to minus j omega. Then instead of t, we can replace it as p plus tau dp. Okay, so we can split that e raised to term into two, that is e raised to minus jp and e raised to minus j omega tau. So e raised to minus j omega tau, you bring that outside the bracket because that is a constant with respect to that integration, because integration is with respect to p. So what you see inside the bracket is nothing but x2 of j omega, because p is simply a dummy variable. You can see anytime you can replace that p with t. So that is x2 of j omega. And what is the remaining terms? Remaining terms is nothing but minus infinity, integration from minus infinity to infinity, x1 of tau e raised to minus j omega tau d tau. Again, you can see that tau is a dummy variable. You can anytime replace that tau with t. So that is nothing but x1 of j. So the Fourier transform of two signals convolved in time domain, that is x1 of t convolved with x2 of t, is nothing but x1 of j omega multiplied by x2 of j omega. So in the same sense, you can easily understand what is multiplication property. That is what happens if you multiply. Okay, sorry, there is a mistake there. That is 1 by 2 pi. Sorry, see. Okay. That is a mistake there. You please correct that. That is 1 by, that is if x1 of t tends to x1 of j omega, and if x2 of t tends to x2 of j omega, then if you convolve two signals in frequency domain, that is why I told that there is a mistake. That is why it is nothing but 1 by 2 pi x1 of j omega convolved with, there is a star signal coming between x1 of j omega and x2 of j omega. By mistake I have left it, I have missed that. So if you convolve two signals in frequency domain, that is x1 of j omega convolved with x2 of j omega, and if you multiply that with 1 by 2 pi, what is the result? That is simply x1 of t multiplied by x2 of t in time domain. Okay, so same thing, same arguments, whatever we have seen, whatever techniques we have used in the derivation of the convolution property explained in property 7, that all techniques we are using here, you can simply go through the derivation and easily understand. Okay, and that is the result. That is 1 by 2 pi x1 of j omega convolved with x2 of j omega will be nothing but x1 of t multiplied by x2 of t. Simple multiplication of two signals in time domain. Very important result. Okay, then the modulation property, again result is very important. That is you have a message, that is a message signal, that is x of t, that is modulated with a carrier signal cos omega c t. That cosine signal is a carrier wave with a frequency omega c, and so x of t is being modulated with the carrier waveform with a frequency omega c. Then what is, if you find the Fourier transform of such a modulated signal, then what is the result? The result is half x of j omega minus omega plus x of j omega plus omega c. So that is a very important result. Similarly, if you have a modulated signal of x of t sine omega ct, then this is the result. That is 1 by 2 j x of j omega minus omega c minus x of j omega plus omega c. Okay, then conjugation properties, that's a very important property. That is, if x of t leads to x of j omega, then x conjugate of x of t conjugate. What is the Fourier transform of that? That is nothing but x conjugate minus omega. So what is conjugate? Conjugate is nothing but, for a physical signal, for a real signal, conjugate of a signal of a conjugate of a real signal will remain the same because it has only the magnitude part. But we have a complex signal like e raised to j omega t. E raised to j omega t is a complex signal. So what is a conjugate of such a complex signal? E raised to, for complex, e raised to j omega t conjugate is nothing but e raised to minus j omega t. So what is the conjugate of e raised to minus j omega t? That is nothing but e raised to j omega t. So for a complex signal, the sign of the j term changes. That is the importance of conjugate. Okay. So by definition, x of j omega, we know what is that. and then we find the conjugate of x of j omega. That is nothing but the integration we take, that integration we take inside a square bracket. The whole integration is under conjugation, that is star. The whole integration raised to the star. Okay, now we take the conjugate inside that square bracket. Then we have integration from minus infinity to infinity x star of t. Then if we take the conjugate of e raised to minus j omega t, that is nothing but e raised to j omega t dt. Okay, now replacing omega by minus omega, you simply replace omega by minus omega. So that is RHS x star of minus j omega t. Why minus j omega? Because we are replacing omega by minus omega. Now in the RHS side, integration from minus infinity to infinity x star of t, we have replaced omega by minus omega t. So it becomes e raised to minus j omega t dt. So that means it is nothing but the signal is now x star of t. So it is nothing but the Fourier transform of x star of t. So the Fourier transform of x star of t is nothing but x star of the capital X star of minus j omega. That's the result. Now a very important result, that is Parsifal's theorem. That is, if x1 of t leads to x1 of j omega, and if x2 of t leads to x2 of j omega, and if you find integration, if you find the integration of x1 of t and x2 of x2 star of t dt, then that is nothing but 1 by 2 pi minus infinity to infinity integration x1 of j omega x2 star of x2 conjugate of j omega d omega. That is for two complex signals x1 of t and x2 of t. Suppose we have two suppose we have x1 of t equal to x2 of t, then that becomes integration from minus infinity to infinity modulation of x of x, the magnitude square of x2 of x of t dt equal to 1 by 2 pi, then integration from minus infinity to infinity magnitude square of x of j omega d omega. So what is the inference of that? The inference of that is nothing but the energy of the signal, whether in time domain, will be equal to the energy of the signal in frequency domain. So energy of a signal in time domain will be equal to the energy of the signal in frequency domain. The derivation also is very simple. You can just go through that. The same techniques, that is, we change the order of integration and we find that, then we apply the conjugation and everything. We can simply understand just 3 steps. Okay, so these are the things you have to learn. This Parsifal theorem is very important, and derivation is also very important with respect to university examination. Okay, so these are the properties, very important properties of Fourier transform, and in the next section we'll apply the different properties in the problem session. Okay, thank you.